I just want to emphasize, because Prof. Raju just sent an email to all of you, just to emphasize for my part, okay, so CA2, what covered in CA2 is not needed anymore. So for day CA3, only last 2 weeks is needed, plus this tutorial. Okay, so before COVID, I always bring some glass slides to the tutorial room and ask challenge students to try it. So like, because myself is, I do a lot of research on smart window. So in my lab, students always need to cut this like a glass slide into half. So how can we do so? So do you have any thoughts here, Jingxiang? Have you done any thoughts here? Okay, so actually this one is pretty much use this, what we call it, use this one. Griffiths. So how does this Griffiths mean here? So let me change the color. Okay, for example, right, so this is your gut slides. Okay, so if I want cut into 2, so basically I use a very like sharp diamond scrap. Like a diamond scrap, just put a scratch on the top first. You know, diamond, right? Diamond is harder than the glass, so use a diamond scrap. So diamond is more or less like it's a very pointed shape of this cutter, like something like this, but they're coated with diamond here. Okay, so then I just simply use this one, more or less like a needle. So I'm trying to create a surface crack first. Okay, so as I said before, so glass is the most typical Griffiths materials. Okay, so glass is the easiest one to get fractured, or the most brittle materials. Okay, so that's a Griffiths case. Okay, so what can we do? So basically after this one, I use a very, very small force. I just bend it very slightly, so can cut this one into 2 already. So if I want cut here, so you can just cut here. Okay, you can just cut here. Okay, so then because this surface crack is just on the surface. Okay, but after you crack it, you will start from the surface all the way through the bottom. Okay, so that is a very useful way when you do your research, if you are related with glass or windows or whatever in your FYP. So you can use these small tricks in the lab, because obviously, so no lab can provide you with all this laser machine, right? So otherwise you need to use laser to cut, but it's almost impossible to do it in the lab. Okay, so they will not be so rich can provide the laser for you to cut. So we have these small tricks to do it in our own lab. So that's what we have done. Okay, so the Griffiths means you have so no matter what, for Griffiths, right, you just create a little bit small crack on the surface, then just use a very small force. You can just cut all the way through this surface to the other side, which break into 2, something like this. Okay. So that is one of the practical way we can use it in the research lab in your FYP. Okay, so this one, because we use the concept of Griffiths, and also we know it applies very well to the glass, and glass is the most brittle materials. Okay, so let's continue. Okay, so this is the last tutorial, as I said. Okay, and it is going to be included in the examination. So, and also it's not simple questions here. Okay, a lot of it need a lot of thinking here. Okay, so as I said, I help you to summarize the most important questions of this course, of this part already. So these 7 questions. Okay, 7 questions. Okay, so let's start one by one. How does fracture happen? How big is the force? Okay, so as I promised you, I give you these questions. Okay, so a lot of conditions has already been given. Okay, so with a given graph, provide the relationship between Young's modulus y and maximum stress sigma, and the sigma equal to y/8. Note that typical most bound will fail when they're stretched by about 25%. Okay, so this is a derivation questions, so which will not be covered, will not be required in your final exam, in your CA3, but it is a very important concept questions. Okay, so we use this graph and help you to review what you learned before in your year 2, and also come up with everything, just combine all the concepts together for you, don't confuse them. Okay, because I realize students are very easy to confuse with the concept here. Okay, So let's see. So this is the F. This is F. This is R. So as I said before, right? So this is two atoms. So the distance between the two atoms. So when it's at R naught here, so which is this point, which means you don't have compressive stress or no tensile stress. So at this stage, we call it it's a stress-free state. Stress-free state in most cases is the most happiest state for any materials. Okay, so this is stress-free state. Okay, so since we ask you to calculate the stress, strain, everything, and also Young's modulus, surface tension, everything. So let's just try to put all these equations we had learned before. So sigma is a stress, right? So we learned this before. So Y, Young's modulus, strain. Okay, so and also the stress equals to force over area. Force over area. So you can see here we only have force, right? We have force. Okay, force over area. So you need to figure out what is area here. Okay, something which is unknown. Okay, so strain is a little bit easier. So L minus L naught over L naught. So you can imagine now I have at the very beginning, the distance between this atom is R naught, right? So when I reach until blah, 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 until here, which is this R fair, okay? So which means this one is going to fair, okay? So this R naught and change to R fair, okay? So it's going to fair it. So anyway, during this process, right, you just keep make it bigger and bigger and bigger and bigger until we reach this point, okay? So this is strain. And also the most important thing here, we have to be careful because it is related with elastic deformation and plastic deformation. But we always, for ceramic, right, we always at the very beginning, at this region, this beginning, we assume it is a elastic deformation, and it is true at the very, very beginning. So that's what we said in the vicinity of R naught. Okay, so at any place, so this S naught we call it a stiffness. So you learn in your year 2, okay, but I just help you to summarize here. So S naught equals to dF over dr. So dF, which is dy, right? dy over dx. dr is here, okay? So dF over dr when r is equals to R naught, okay? So which means, but the thing is, the good thing is, because as we said at the very beginning, so this one, it is an elastic deformation. So once it's elastic deformation, so dF over dr equals to what? dF over dr equals to, this is a year 1 mass, year 1 mass here. So since it's a linear relationship, right? Linear relationship is very easy. Okay, how can we determine the dF over dr, which is dy over dx? It simply just equals to the what? Can you type? You shouldn't return all your maths and all the fundamentals to your lectures. Okay. Okay, so how can we determine this S naught here, dF over dr? Okay, for example, I have this coordinates, which is x1, y1. Okay, then I have x2, y2. Okay, so how can I determine this? Actually, it's the, let me see, any student. Yes, leader gradient. It's a slope. Very good. It's a slope. Okay, very good. So for example, I have this point. I have 2 points, right? This point is x1, y1, and this is x2, y2. Okay, so how can we determine it? So simply, it's just a y2, as Lida said here. I think Lida got it correctly. Thank you very much. So basically, it's just a y2 minus y1 divided by x2 minus x1, right? Because it's a linear relationship. This only applies for the linear relationship, okay? So that's what we said for the Fourier approximation. So then we know the F equals to S naught R minus R naught. So how can we derive here? So since maybe it's a bit messy here now, so let me just restart. Okay. Rotate. I notate, I should use, it's better I still use my own way. It's this way. Why every time change color? Okay, so we said since this one at the very beginning, remember all the conditions. Every time you do any derivation, remember the conditions. So we put in the vicinity because it's at very beginning. So it's a linear relationship. So it's just a linear line, straight line. So for example, so I put a 1 point here. point here. Okay, so for example, put 1 point here. So this point, right? So then you know the x, which is r, right? X, which is r. Okay, y, which is f, right? Y, which is f. Okay, but how about this point? How about this point? This point, what is x here? Can you type? What is x here? Can you type, please? Yes, very good, very good. Arno, right? Thank you, leader. So Arno and y, which is 0, right? Okay, so as I just said, so S no is equals to y minus y, x minus x, right? So which will be f minus 0, r minus r no. Okay, so that is what we have seen here. Okay, this is approximation. F equals to S no equals to r minus r no. Okay, so this is a stiffness. Don't confuse. Stiffness is dy over dx. Dy over dx. Okay, so which means the unit length. In order for the material change the unit length, you need this unit force. Okay, so that's a stiffness. So let's continue. Okay, we have force already, right? Happy. So because we need a Young's modulus here. Okay, Young's modulus. Okay, and also force. We have area. Okay, so let's continue. Okay, so typically most bound will fail from as the stretch by 25%. So which means what? Which means your R fair, what's the relationship between the R fair and R no? So which is 1.25, right? R fair is equals to 1.25 of R no, right? Because I stretch about 25%, it's going to fair. Typically, most bound will fair from the stretch by about 25%. This was given by this question. It is conditioned there. Okay, so and also I give you another triangle here. So which is this triangle, which is this dotted line. This is dotted line. Okay, so this dotted line have another triangle here, and also this slope. This slope actually, because this is a bit exaggeration, but this slope is actually the same as the slope we just mentioned here. Okay, it's the same thing. Okay, so this is another approximation. So this S no, which is also what we can get from this line, the slope of this line. Okay, so how can we get the slope of this line? So obviously this was given by this question. Okay, so again is y minus y, x minus x, as Lida said. Okay, so what is this x now? This point, what is this point? This x is what? In this case, the x is R fair, right? And y it is 2f maxima. 2f maxima. Okay, this is x and y. And also for this orange point is still the R no 0, right? Same thing, same thing. Okay, so we can have another approximation, which is from this dotted triangle, which was given by me by this question. Okay, so the S no, now again, you have y minus y. Y will be 2f maxima minus 0. Okay, R fair minus R no. So, and also I know that R fair is equals to 1.25 R no minus R no, right? 1.25, replace this R fair. So then in the end, I will have, you can say, ooh, are you happy? You see some 8 already. Happy, right? Wow, very nice. You see the 8, very close to what we're trying to prove. So 8, F maxima, no. F maxima, no. Okay. But now, since we are talking about the relationship between the Young's modulus, so the F maxima is not enough anymore, right? We have to change to the sigma. So the relationship between the sigma and the F is equals to sigma equals to F over area. F over area. Okay, so this is a little bit tricky here. So can you please be patient here? Okay, so in this whole graph, right, which is LGO potential, we simply assume that atom is arranged in such a way. Something like this. Something like this. Okay. Okay, the atom is arranged in a perfect way like this. Okay, so can you imagine now if I give them a stretch like this, perpendicular to this plane of this computer? Okay, so what is the area of one atoms, of this particular one atoms? It stand. The area of one, because every time now we are calculating is one atoms, right? It's all about one atom, because what we are calculating here Can you type now? What they're calculating here is a theoretic value or is a practical value? Can you type? It is a theoretic value or the practical value. Very good, Shumpei. Very good, excellent. It's a theoretic value, Okay, so this is theoretic value. Okay, so since now what is area now? So we have learned a lot of tricks before, right? How can we, as a whole, how can we just distribute to one atoms? How can we determine it? Okay, so there's a way to do it. Okay, so for example, I put it here. So for example, this is one atom, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 atoms altogether, right? So for just one atoms, so if I distribute everything uniformly, so how many areas will be distributed to these little atoms here? So you can just simply do this, right? This is the easiest one. This is the most fair one, right? Each of them was given a square. Easy. So this is the easiest one to, and also even distribute among all of them for one atoms. Correct, right? Correct. Okay. So now you tell me, so what is this length? What is this length? What is this length? So the distance between the atoms, between atoms is R naught, right? R naught. Distance between R naught. Okay, so now I just, this side I have half R naught, right? Okay, so which means this is half R naught, this is also half R naught, this is half R naught, this is half R naught, half R naught, half R naught, and half R naught, and half R naught. So in the end, it's simply just a square, okay, distributed to these atoms as a effective area. Okay, again, this is approximation, okay, so we can go back now. We can go back. So Young's modulus equals to this stress over strain. Stress over strain. So we also said stress equals to force over area. So just now we already derived the area is R naught square. Am I correct? Okay, and the strain, as we already said, strain, we simply use this one, which is R minus R naught over R naught, right? So R naught is original one. R minus R naught over R naught, correct? Okay, so I just use the equation here, force over area. So area we just said for each atoms, so you're supposed to stand about R naught square of the area of each for one atoms, okay? So then you can see here, right? So what we can do here, so if we use this equation we have derived before here, F equals to S naught over R times this R minus R naught. So then I know this one is equals to what? F over R minus R naught equals to what? F over R minus R naught. Very good, Chopin, very good. You're very quick with math here. Okay, very good. So S naught here, right? So S naught. And also R naught square over R naught. So you're going to have R naught here. Okay, so that is all. You're happy, right? You have Young's modulus come out already. So very happy. So now we're very close to the relationship between the Young's modulus and the force. Okay, so then we put everything back there. So you can see, so this sigma here, so you can see, put this one back, I'll put this one back here. So I can continue 8 F maximum over R naught, right? But I still have one more R naught here, right? R naught, so that, which means this one is square. Okay, is it clear? It's a bit messy here. Now I just discard. Let me continue. Okay, so you can see I use equations, Young's modulus, sigma over string, and sigma is F over R naught square, and string is R minus R naught over R naught, right? And also then we already know that this F over R minus R naught, it is equals to S naught, right? S naught, then this R naught square here, and also R naught here. In the end, you only have one more R naught here. Okay, so far very good. So then I also have the S naught derived from the previous one. So which means in the end, I can put 2 F maximum Okay, then I have one Arnold here, and also have another Arnold here. So Arnold square, which is simply, as we said before, Arnold square is simply just the area. So we assume that this is a simple approximation because ceramic, right? Ceramic, you actually, when you change, the change is not that much, just a little bit, okay? So Arnold square. So F maximum over Arnold square. So this one is, which is F over area, which is going to be the sigma maximum. Sigma maximum, okay? So then you can get this one, the sigma maximum equals to Y over 8. Okay, with all these given equations and given geometries which was given by this question, we can prove that sigma maximum is going to be equals to roughly about 10% of Young's modulus. So as what we stated in your notes, we said, so theoretically, so the maximum stress is going to be 10% of the Young's modulus. Okay, but of course, from this geometry given here is 8. So Y over 8, Y over 10 doesn't matter because in most material science, we always talk about magnitude. So roughly that, which means if your, for example, like glass, right? So for example, if your Young's modulus is 60 gigapascal, 60 gigapascal, okay, which means your theoretic strings will be 6 gigapascal, right? If I divide it by 10, which will be 6 gigapascal. If I divide it by 8, so it's roughly, it's 7 point something, right? 7 point something, 7.5, something. Okay, doesn't matter. I mean, in this range, okay, but the actual thing for glass, it is only megapascal. It will never be gigapascal. Okay, so it's even less than 10% of this value, which means even less than 0.6 gigapascal. So my next question is why the practical value and the theoretic value varies so much, So can you type? I'm very sure all of you know this question already. Can you type? Mintan, Shumpei? Yes, very good. Very good. Okay, thank you very much. Okay, so first of all, as I said, although this one is not required, but I just want to help you to clarify what you have learned in your year 2 or year 1. Okay, so don't confuse all this concept. Young's modulus, stress, strain, and this is force over area. And strain is L minus L naught over L naught, and what is stiffness? So all these are different, okay? And also what we learned in our course is toughness. So toughness is not only sigma anymore, it's also not some like a cracked lens anymore, it is a combined thing. Okay, so it's so unique, So I just wanna help you to review what you learned before and more or less put it together. Okay, so let's continue. Okay, so let's come to our second question. So why there's a huge difference between the theoretic value and that's what we see here. The breaking stress predicted by the LGO potential assumes that the whole plane is broken at the same time, which lead to huge exaggerated stress. But the reality is start from the weakest link, which is pre-existing cracks. For example, as I said, your handphone, your computer always have pre-existing pores there already. You just cannot see it by your eyes, but if you put under microscope, you will see it very clearly. So which means your crack is going to propagate from the worst crack. Okay, so that's what we say here. The bound break a few at a time at the tip of growing cracks. Okay, and this now is becoming successive cracks, one by one. We break as a crack propagate. So this will be much easier. Okay, so this is our question 2. Why is there huge discrepancies between the calculated strings and real ones? So we said calculations suggest all bound break at the same time. So that's why you see you use LGO potential, right? We just assume 1 atoms. So then it's add up 1 atoms. Okay, but reality is at the tip of propagating cracks. Okay, so that's question 2. So then what will determine the crack propagate to have failures? Okay, so then there's a very important concept here. So you can see this is question 2. A relative large plate of glass subject to a tensile stress. The stress is 40 megapascal. If the specific surface energy and modulus elasticity is this and this, determine the maximum length of the surface ball that is possible without fracture. So since, first of all, this is glass, right? So as I said, glass is the most perfect Griffiths materials. So it's the one you always need to use this Griffiths criteria, okay? So, so let's see, okay? So this question is actually very similar to what you have seen here, right? So we say hey, this video, this crack is still too small. This crack, again, not big enough. Only when the crack is big, certain size, so it will fail automatically because you just now you see the stress is actually fixed, right? Okay, so that's what the question 3. What is observation of this video? So when the crack exceeding certain size, the crack will propagate catastrophically. So this is exactly this question I'm asking you now. So what is the pre-existing crack size existing on the glass will make it cannot stand the stress, which is 40 megapascal. So in this case, what you're actually calculating, tell me what you're actually calculating. So the maximum length of surface fall is actually what you're calculating. Can you type? What you're calculating here is a very good, very good. Jingshan Shumpei, very good. Yeah, it's a C critical. Excellent, excellent. What you're calculating is actually a C critical. Same as what you're seeing in this video. Let's find the third crack size. Okay, so how can we calculate the crack size? Okay, again, material scientists are always NH change, right? NH change. So we said we have 2 NH. So one is elastic NH release. The other one, you're going to create new surface. So then we also have these 2 curved surface. Is this one where you have one more broken surface, right? Which means you're going to have one more surface NH, right, come out, okay, which means you have more surface, right? So you're also, once you break one more bond, you also release one more elastic NH. So that's 2 portion. So the most important thing is this U total. So if it's too small, so we actually explained this one quite a lot of time already. So we can say too small, nothing happened. Continue this point, nothing happened. Only when you reach this point, the system will know automatically, hey, if I become bigger, I will be very happy. Why is so? Because this U total start to reduce. Okay? Okay, so that's the whole concept. Okay, so as I said, most of the time, I won't require you for all these theoretical calculations or derivations, but why I still teach you a lot, because I think this is quite important for material scientists. This is more or less like common sense for all of us. Okay, so we have derived this one. So mathematically, very simple, use dy over dx, make it equal to 0. So which means you're going to get the maximum point here. This is a very standard math manipulation. So we will get these equations. We do a little bit small modification here. So that's the final answer. The sigma square root pi c is have to equals to square root 2 Young's modulus surface tension. So this is a Griffiths criteria. So Griffiths criteria tells you that your fracture toughness is a fixed value. This is again very important. Why it is a fixed value? Because it is also equals to K1C. It is also not, it is equals to sigma pi c critical, and also it is equals to square root 2 Young's modulus surface tension. That is a Griffiths. That is Griffiths. So now I'm asking you if it's R curve. It is R curve. So do you think this one still okay? This equation is still okay? No, because it is going to increase with the C size. Okay, so let's continue. Okay, so simply use this equation. So it's very simple. Since, as I said, you have this one is a Young's modulus. This one is a surface tension, and you simply, and also you know the sigma here. So you can see you have almost everything except this C critical. So you just do a small mass manipulation here. So you will get C critical equals to 2 Young's modulus surface tension pi sigma square root. Okay, so just do a little bit, just make sure the unit is the same. Okay, unit, I personally always prefer everything changed to Newton meter. Then I won't make mistakes. That's my way. Okay, you have your own way, but doesn't matter. Okay, so you can say 269 times, because it's giga, right? giga. So giga will be 10 power 9, right? Pascal is Newton per square meter, right? And the surface tension is actually just Newton per meter. J per square meter equals to Newton per meter, okay? And also the pi is here. And now the one is a megapascal. Mega is a power 6. Pascal is still Newton per square meter, right? So once you do everything like this, it's almost impossible for you to make mistakes. So after the calculation, I know that 8.2 times 10 minus 6 meters, which is 8.2 micrometers. Okay, so you can see actually the crack is very small. You cannot even see by your eyes. It's only 8.2 microns. That's why, as I said, even though your handphone, everything, right, you have full of cracks on the surface or pores, it's just not big enough. So you won't feel it because all the crack is still smaller than this critical. So that's why it is still safe. Okay, so this is question 2. Question 2. So this is a pretty straightforward question because we use a Griffiths already. So Griffiths just use these equations and expand it and do the math manipulation here. Okay, so that's question 2. Question 2. Okay. Okay, so let's continue. Okay, I help you review. Materials failure come from where? For ceramics, it is very important. It comes from crack tip propagating, which means they start from the critical ones. The most critical ones is going to fail first, and then all the way will open up. Just crack tip propagation. So, and also in the Griffiths, again, this is still only Griffiths. Once the materials break, it will only release the elastic energy and also consume the surface energy. Okay, and also this very important concept so far is this a certain size. Okay, so you cannot be bigger than this one. If it's bigger, so if the stress is big enough, you're going to fail catastrophically. Okay, so that's the take-home points. Okay, so we said, okay, we talk about Griffiths, so we assumed only tensile stress considered, right? So obviously, remember the compressive stress will be much higher than the tensile stress. Okay, and also we only talk about the 2 energy need to be balanced. Only 2 energy need to balance. Okay, so that's a Griffiths assumptions. Okay, so now move to question 6. Question 6. Okay, so since tensile case, which is this case, right? Tensile case is mode 1. Tensile is mode 1. So if the materials is intrinsically weaker in tensile, just like all the ceramics. So ceramic is weaker in tensile compared with shear and the tearing. Okay, so that's why ceramic would prefer to fail in this mode 1 way. So this one is a disaster. Why is so? Why is a disaster for toughness? Can you type the keywords here? Why it is a disaster for toughness? Meantime, Jingshan, Jordan, Leader, Shunpei, Sherry. Just share your thoughts here. Because once you have this tensile mode, which means you won't really have any very good dislocations. Yes, both of you are correct. Shunpei also correct. Okay, positive deformation and dislocation for mode 2 and mode 3. Excellent, excellent, exactly. Okay, if it's just simply open up, you don't really have any like a sliding or sharing or tearing, because all these things is going to help with the dislocation generation and dislocation movement. Okay, and this two is equals to the plasticity, crack tip plasticity. Dislocation generation and dislocation motion. Okay, so then we said ceramics, because tensile is weaker, so then it's going to sustain a sharp crack, and it's a Griffiths, so it's mode 1 case. Okay, so like metal, just weaker in shear, so that we're going to fail in a shear way. So then the dislocation will move away from the crack tip, so which is mode 2 and mode 3. Okay, mode 2 and mode 3. So these two gives you dislocation generation and dislocation motion. Okay, so both of these two things is going to consume extra energy. Okay, So that's a very important concept. Okay, so why ceramic is brittle? So there's not much crack tip plasticity such as dislocation, generation, and motion. And these two will consume. So then you know in the balance, you know which one you go, right? It's release or consume. Okay, so which will consume energy to help to inhibit the crack opening. Okay, crack opening, which means you're going to have more and more new what? Can you type? Crack opening, which means you're going to come up more and more new. Okay, let me see. Surface. Thank you, Mingtan. Excellent. So you get the point already. Okay, so that's what we said. Okay, so in the Griffiths case, so basically you have elastic energy released. Okay, but all these things is used to consumed by a new surface. So this is awful. We don't want this. Okay, because new surface means you're going to near the crack already, right? You don't want it. So let's just trying to do something else, some other ways to consume extra energy. For example, like dislocation generation and the dislocation movement, all this plasticity. Okay, so all these things means here, dislocation means here, this one also means here. Okay, so that is why ceramic is brittle. Okay, so then you know the concept already, right? So the next one, you as a material scientist, you know the science already. So now let's move to the engineering side. So how can we make it not that brittle? Okay, so that's our second question. How to increase the fracture toughness? Okay, let's just make this the green one bigger. So which means this one bigger, this one maybe smaller. Okay, as simple as this. Okay, so let's just create hurdles to inhibit the crack opening or have some extra ways to consume extra energy. Okay, so both ways you can understand this question. Okay, so let's see. This question actually is very, very difficult. Okay, but I just want to see how you answer it. Can you type? So you think group A is winning or group B is winning? It's a very difficult question, actually. So two research groups are competing to fabricate magnesium zirconia. Zirconia, right? Zirconia. So which is this? This little lovely guy here. Okay, and the compensate with higher toughness from the XRD results at room temperature in group A. Zirconia is pure tetractile phase, while in group B, I'm talking about room temperature. While in group B, zirconia is a mixture of tetractile and monoclinic phase. So which group do you think have produced higher toughness? So now I'm asking you keywords here. Higher toughness coming from where? Can you type your keywords? Let me test your understanding here. The higher toughness of zirconia coming from where? Mingtan said B, Sherry said B, Jinshan said A. Jordan said need more metal stable tetractile phase. Excellent. Jordan and Champagne mentioned about important thing here, which is the phase transformation. Phase transformation. Okay, so now let's go back. Okay, so the toughening mechanism, what's the name for this one? The name for this one is what? The name for this one is transformation toughening. Okay, so this is so important. So if you don't have transformation, you won't have toughening. Okay, so Champagne and Jordan make a very, very important statement here. Correct. Please make sure you have more transformation. Okay, so how transformation is going to help? Okay, so let's see one by one, right? So first of all, so we said, okay, welcome this one. Okay, so we said zirconia. Zirconia is a very special thing. Okay, so at room temperature, it is monoclinic, and also it's bigger, and this is room temperature. Okay, there's a high temperature and a smaller. Okay, so monoclinic and tetractile. Okay, if you heat up more than like 1170 degrees, so it will become a tetragonal. Okay, so the thing is, if this zirconia is standard known, right? Standard known. So if you raise up temperature to 1,000, like 1,170, so it will become tetragonal. If you cool down, you will go back to the monoclinic. Am I correct, right? So that's a thermodynamic stable, which means it's the happiest state, which means it's a minimal energy state. Okay. So, but the thing is, now the zirconia is serving as a slave. It has been constrained by the matrix. So in our question, I'm asking you, is the slave driver is magnesium. Okay, so now let's say, for example, the matrix everywhere is magnesium. Okay. So for example, because okay, now at the higher temperature, it is still tetragonal, right? But the thing is, if I cool down, okay, tetragonal is smaller. If you go back to room temperature, it's supposed to become bigger. Am I correct? Okay, but the thing is, it has been constrained by the matrix. So now, even at room temperature, that's what we put here, find tetragonal particles at high temperature, because at high temperature, tetragonal, right? If you cool down, it's actually constrained by the matrix. Which means you cannot go back to monoclinic. Okay? Cannot be bigger. You can only stay as a small little guy here. That's what we put here. The original metal stable tetragonal phase here. Okay, so even at room temperature, you retain as metal stable tetragonal phase. Okay, so far so good. So far so good, right? Okay, so that's why I say I keep highlighting metal stable tetragonal phase. Oh, so that is from your process, right? Your process, you did some smart thing, make sure your materials have a lot metal stable tetragonal phase. Now let's see if crack coming, okay, for example, you can see this one, the crack coming, right? So crack means what? Crack means it's a liberator. Crack liberator means you peel off the constraint, right? Because the matrix is get peeled off. So which means now your particles actually is not under, is loose constraint. Loose constraint means because now it's room temperature, right? Room temperature, which means you're happy to go back to where? Happy to go back to monoclinic phase. Okay, so once it loose constraint, so you're going to change from the tetragonal phase, metal stable tetragonal phase, to monoclinic. Okay, so this is a phase transformation. Okay, so that's why you can see just near this region, which is a crack coming region, you can see there's a double line here now. Double line, which means what? Double line, which means it's become bigger because monoclinic is bigger. Okay, so which means, okay, suddenly you can imagine before, right, this region is small, but now you have to become bigger, which means you're going to give a lot of compressive stress, yeah, to the crack, to stop the crack to propagate. Am I correct? So you just imagine if you stand here, right, as a person, you stand here. Okay, so now if someone want to go through, like a crack goes through, right? So for example, so this is case A. So do you think, compare with, I have a two big guy here, maybe two big guy here, and two big guy here. Okay, now you still want to go through. Okay, so which one is easier, A or B? Easier, I'm talking about easier. So obviously the, you go through to a slim guy will be much easier, right? Because now this one become bigger, okay? So this phase transformation coming from the 4% volume expansion. So this is going to give them a very high compressive stress. So high compressive stress is going to give you extra energy needed to extend the crack. So this is going to enhance toughness. Okay, so the keywords as you summarized, okay, by all of you, Jordan, Nida, and Chopin, all of you summarized correctly. Exactly, that's what you said. If you want more toughness, you want more of this become bigger, yes or no? So if you want more toughness, which means you want more compressive stress, right? You want more compressive stress, so you want more of this little guy become phase transformed, correct, right? So the basic concept here is the more phase, the more the merrier. Okay, the more phase transformation, the higher toughness. Okay, so that is a concept. Okay, so that's what I put here. So if it's stress-free, right? So zirconia, a happy state, which means it is a stress-free, no tensile, no compressive, right? So higher temperature is tetragonal, room temperature is monoclinic, is bigger, right? But if this little guy has been constrained, not happy, right? I have exam, I hate it, right? I cool down, so I still a small guy here. Even at room temperature, I'm still a small guy here. Okay, I'm not happy, right? Because it's metastable, which means it's not happy state. Okay, but now if I peel off this yellow constraint, I free you. So which means this one, the crack give free surface, peel off this yellow one. So it's go back to this monoclinic phase, will become bigger. Okay, so this is another way for you to understand it. So once this one become bigger, so you're going to give them a lot of compressive stress, which means you're going to have enhanced toughness. Okay, so the concept and essence here, it is the more the merrier. Okay, so sample A, to get higher toughness, we need more metastable tetragonal phase. Okay, so obviously this one is very difficult. Why? Why it is difficult to get so much tetragonal phase? Because, okay, you always need to remember, right? So materials, if possible, always want to go back to the metastable or stable phase time. Can you type? If possible. Yes, they always prefer to go back to a stable phase, right? So which means actually it's very, very difficult for you to get more and more pure tetragonal phase at room temperature. Am I correct? Because this is not a thermodynamic stable phase. Okay, so it's very difficult. Actually, what I put here is not something like I just put a theoretical question here. It has been achieved by one of the MIT group. Okay, so they have a patent here. They have used some tricks to make sure the whole bulk materials is full of pure tetragonal phase. So it's not something simple. It is something very difficult, but it is doable. So if you understand the concept behind it, so then you will understand why this MIT group trying so hard to patent this whole thing, make everywhere zirconia, even at room temperature, it is still tetragonal phase. Okay, so that is the question 3. Question 3. Also, the answer here, I look simple, right? But you have to give me the full answer. Why? So why this phase transformation is going to give you the toughness? Okay. So that's a question 3. Question 3. Okay. Okay. As I said, it's not a simple question. It's difficult question. Okay. Okay. Question 3. So the last question, to investigate effects of crack size on the strengths of the ceramics, different journeying time at high sintering for 3 samples, ABC. Okay, I summarize here. The data consists with Griffiths criteria R curve. So what's your answer here? Is R curve or Griffiths? Can you type? So how can we determine whether something, this materials is with Griffiths or with R curve? So how can you determine it? So simply just calculate the K1C, which is toughness. So if, for example, if my curve, if I put X here, and this is Y. So if I said, if this K1C is not dependent, which means it's always a straight line with the crack size. So we said it is a what? It is a Griffiths, right? Because it's going to equals to 2 Young's modulus surface tension. Okay, 2y surface tension. Okay, so this is a Griffiths. Okay, but if it's if you realize, okay, so you give them different crack size and you find the K1C is actually increasing. Since it's increasing, so this one is no longer the Griffiths anymore. Okay, so it is R curve. So, okay, so can you just really type down the important concept here? So Griffiths criteria refers to super brittle case, brittle. And the fracture toughness is a fixed value. But if it's R curve, it is a toughened case, which means it becomes toughened, which means your K1C or the toughness is not a fixed value anymore. Okay, so how can we understand this one? So we said R curve refers to fracture toughness increase with this. Okay, but Griffiths is the fixed value. So why is so? So I have give you I have done an animation, right? But anyway, I will send this slide to you. Okay, so you can see at the very beginning, right? Nothing stop here, right? So it's constant, constant, constant. That's why at the very beginning is constant. Okay, so then if I reach this point, toughened. There's a strong enemy here. Stop, stop. Okay, so this is first element, second element, three elements. So when you come to the third, the third element, right, which filament. So the first one, the second one, you still have the effect. Am I correct? So when the crack reaches the ligament, the energy need to propagate will increase per unit length because the ligament introduce additional area, additional surface area, and may be pulled out. Okay, so this will cause the increase of the toughness. That's why, right? Because it keep increasing. Okay, but now you can see this first one, right? So this first one, it has dropped out already, right? Because this is larger than the length already. So as more and more ligament become affected by the crack, the fracture toughness will continue to increase, but at a reduced rate. Why is so? Because some of the initial ones won't take effects. Okay, so that's what we, especially right, like this one is very obvious, right? This one, all this drop out already. The first man now drop out completely since the crack width have surpassed. This is crack width. Crack width surpassed the ligament length. The fracture toughness will now a constant value. So okay, so since all the new filament is going to have effects, but all the old ones is not there anymore. It's not going to accumulate the toughening effects anymore. Okay, so that is if you really want to use animation, help you to understand what is R curve. So more or less, this is a good way for you to understand it. Okay, R curve. So if we go back, so if we can show the critical stress intensity factor is a constant, so it's a Griffiths. If it's increasing with crack size, it's R curve, right? So this is principle, very simple, right? So I'm just very lazy, okay, because the question I asked you is very simple, right? Ask you whether it's a R curve or it's a Griffiths. So I even can't be bothered with the unit, okay? But okay, if in the examination, if I ask you to calculate, so you have to give me all these correct unit. I'm just very lazy here, okay? So the first one, the size actually is a micron, right? But I just put 16. Sigma is this, sigma is this, sigma is this. So each of them you can see when the crack size increased from 16 to 100. So you can see the toughness actually increased from 600 to 1,1200, right? So it's nearly doubled. So obviously this is not a fixed value, right? Since it's not a fixed value, so we say, hey, it is a curve. So we can see that critical stress intensity factor is increasing with increasing, crack size, okay? Which means with increasing floor size, it is a curve, okay? So I'm going to give you the answer later, okay? Don't worry. Okay, so summary is fracture toughness is related with work, extent, a crack. So obviously you give them more hurdles, give them more things to stop them to propagate. So you're going to have enhanced toughness. So the most brittle one is glass. So only have 2 energy need to rebalance, right? Okay, and the fracture toughness can be enhanced by increasing energy required. So most of them, for example, like crack bridging, martensitic transformation, all these things is going to enhance toughness. Okay, so that's the summaries. Okay, so that is all for today. So, and also tomorrow, what time? Tomorrow, 3:30. So there will be a math tutorial. Okay, please do come. So if you need more clarification and more understanding, and also you please join the math tutorial. Okay, so this help you with a CA3. Again, just to emphasize, don't confuse by Prof. Raju's email. Okay, so my part only test these 2 weeks. Okay, and also the derivation of the equations are not required. Okay, all these things, as I said, is not required, but I thought it's good for you to not confuse with what you learned before. Okay, so I stop recording now.